Welcome back to the channel. As we move forward with Model 4, in this session, we'll take an in-depth look at unsupervised machine learning, focusing on clustering techniques and their practical applications. Throughout this presentation, we'll dive into the fascinating world of pattern discovery in unlabeled data, examining how machines can identify structure without explicit guidance. We'll cover essential clustering algorithms, evaluation methods, and real-world examples that demonstrate the power of unsupervised learning across various domains. By the end, you'll have a solid foundation in these techniques and be ready to apply them to your own data science challenges. What is unsupervised learning? Definition: a type of machine learning where algorithms find patterns in unlabeled data without explicit instructions on what to look for. The system must discover structure through self-organization of the data. Key characteristics: works with unlabeled data, focuses on finding hidden patterns, requires minimal human supervision, and emphasizes data exploration rather than prediction based on known outcomes. Common applications: customer segmentation for targeted marketing, anomaly detection in cybersecurity, market basket analysis for retail, dimensionality reduction, and feature extraction from complex datasets. Unlike supervised learning, which requires labeled examples to train on, unsupervised learning algorithms must discover the inherent structure within data. This makes them particularly valuable when working with large, unlabeled datasets where manual annotation would be impractical or impossible. Clustering, the foundation of unsupervised learning. Clustering algorithms. K-means, hierarchical, density-based spatial clustering of applications with noise, and more. Similarity measures. Euclidean, Manhattan, cosine distances. Goal of clustering: group similar objects together while separating dissimilar ones. Clustering forms the backbone of unsupervised learning by organizing data points into meaningful groups based on their inherent similarities. The effectiveness of clustering depends on choosing appropriate similarity measures that capture the relevant relationships in your data. Different algorithms make different assumptions about what constitutes a cluster, leading to varied results on the same dataset. Understanding these differences is crucial for selecting the right approach for your specific problem. K-means clustering, simplicity and efficiency. Choose K clusters. Select the number of clusters to partition the data into. Initialize centroids. Randomly place K centroids in the data space. Assign points. Group each data point with the nearest centroid. Update centroids. Recalculate centroids as the mean of all points in each cluster. Iterate until convergence. Repeat assignment and update steps until minimal changes occur. K-means is one of the most popular clustering algorithms due to its simplicity and computational efficiency. It excels at finding spherical clusters of similar sizes and works well when the number of clusters is known or can be estimated reasonably. K-means in action, customer segmentation. In retail, K-means clustering helps identify distinct customer segments based on purchasing behavior. By analyzing metrics like purchase frequency, average spend, and product categories, retailers can discover natural groupings among their customers. For example, the clustering might reveal segments such as frequent small spenders, occasional big spenders, and loyal mid-range customers. These insights enable personalized marketing strategies, targeted promotions, and improved customer experience tailored to each segment's preferences. Hierarchical clustering, building a tree of relationships. Agglomerative, bottom-up. Starts with each data point as a separate cluster and progressively merges the closest pairs until all points belong to one cluster. Steps: start with n clusters, one per data point. Merge the two closest clusters. Update distances between the new cluster and others. Repeat until only one cluster remains. Divisive, top-down. Begins with all data points in a single cluster and recursively splits into smaller clusters. Steps: start with one cluster containing all points. Split the cluster into two dissimilar groups. Select a cluster to split further. Repeat until each point is its own cluster. Hierarchical clustering creates a multi-level tree structure, called a dendrogram, that shows relationships at different scales. This approach is particularly valuable when the data has an inherent hierarchical structure or when you want to explore clustering at multiple levels of granularity. Dendrogram interpretation, reading the tree. Examine the tree structure. The dendrogram represents the entire clustering process. The y-axis shows the distance or dissimilarity at which clusters are merged. Identify natural clusters. Look for long vertical branches, which indicate significant distances between merged clusters. These represent natural separation points. Cut the tree. Draw a horizontal line through the dendrogram to create clusters. Points connected below the line belong to the same cluster. Validate results. Examine the resulting clusters for meaningful patterns and adjust the cut height to find the optimal number of clusters. Dendrograms provide a visual representation of the hierarchical clustering process, making it easier to determine the appropriate number of clusters and understand relationships between data points. The height at which branches merge indicates the dissimilarity between clusters. DBSCAN, density-based spatial clustering. Density-based approach. Clusters are defined as dense regions separated by sparser areas, allowing for the discovery of arbitrarily shaped clusters rather than just spherical ones. Key parameters. Epsilon, maximum distance between 2 points to be considered neighbors. Min points, minimum number of points required to form a dense region. Advantages. No need to specify the number of clusters beforehand, effectively handles noise and outliers, discovers clusters of arbitrary shapes and sizes. Limitations. Struggles with varying densities across the dataset, sensitive to parameter settings, computationally more expensive than k-means for large datasets. DBSCAN excels in scenarios where clusters have irregular shapes or when noise identification is crucial. Unlike k-means, it doesn't assume that clusters are convex or of similar sizes, making it more flexible for complex data distributions. DBSCAN application, geographic clustering. Crime hotspot detection. DBSCAN can identify areas with high crime density while filtering out isolated incidents. Law enforcement agencies use these insights for resource allocation and preventive policing strategies. Customer distribution analysis. Retailers analyze customer address data to identify natural geographic clusters, helping determine optimal locations for new stores or targeted marketing campaigns. Epidemic monitoring. Public health officials use DBSCAN to track disease outbreaks by identifying unusual clusters of cases, enabling rapid response and containment measures. Geographic clustering with DBSCAN offers valuable insights across various domains by identifying natural spatial patterns. The algorithm's ability to handle noise and discover irregularly shaped clusters makes it particularly suited for spatial data analysis. Evaluating clustering performance. Internal validation. Measures based solely on the dataset and clustering result without external information. External validation. Compares clustering results with known class labels, when available. Relative validation. Compares different clustering algorithms or parameter settings. Visual assessment. Human evaluation of clustering results through visualizations. Evaluating clustering performance is challenging since unsupervised learning lacks ground truth labels. Internal validation measures assess properties like cohesion, how close objects within a cluster are, and separation, how distinct clusters are from each other. When some labeled data is available, external validation metrics can provide additional insights. In practice, a combination of quantitative metrics and qualitative assessment often yields the most reliable evaluation. Silhouette score, measuring cluster quality. Calculate A of I. Average distance between point I and all other points in its cluster. Calculate B of I. Average distance between point I and all points in the nearest cluster. Compute silhouette S of I. S of I equals B of I minus A of I, divided by the maximum of A of I and B of I. Average all silhouettes. Overall score is the mean of all individual silhouette values. The silhouette score measures how similar an object is to its own cluster compared to other clusters. Values range from -1 to 1, where higher scores indicate better defined clusters. A silhouette score near 1 means data points are well matched to their clusters and poorly matched to neighboring clusters. This metric helps evaluate the optimal number of clusters by comparing silhouette scores across different clustering configurations. It's particularly useful for algorithms like k-means where the number of clusters must be specified in advance. Other clustering evaluation metrics. Davies Bouldin Index. Description. Average similarity between clusters, where similarity is the ratio of within cluster distances to between cluster distances. Range. Greater than or equal to 0. Ideal value. Lower is better. Hierarchical Index. Description. Ratio of between cluster variance to within cluster variance. Range. Greater than or equal to 0. Ideal value. Higher is better. Bouldin Index. Description. Ratio of the minimum intercluster distance to the maximum intracluster distance. Range. Greater than or equal to 0. Ideal value. Higher is better. Adjusted rand index. Description. Measures the similarity between two data clusterings, adjusted for chance. Range. -1 to 1. Ideal value. Closer to 1. Beyond the silhouette score, several other metrics help evaluate clustering quality from different perspectives. The Davies, Bouldin, and Hierarchical indices focus on cluster separation and compactness, while the adjusted rand index is useful when ground truth labels are available for comparison. When selecting evaluation metrics, consider your specific goals and data characteristics. Using multiple complementary metrics often provides a more comprehensive assessment of clustering performance. The elbow method, finding optimal k. The elbow method helps determine the optimal number of clusters for k-means by plotting the within cluster sum of squares against different values of k. As k increases, WCSS always decreases, but the rate of decrease changes significantly at the elbow point. This point represents the value of k where adding more clusters provides diminishing returns. In our example, the elbow occurs around k equals 4, suggesting this is a reasonable number of clusters for this dataset. While useful, the elbow method should be combined with domain knowledge and other evaluation metrics for robust cluster selection. Real-world applications of clustering. Retail. Customer segmentation for personalized marketing, inventory management based on purchasing patterns, store layout optimization through basket analysis. Healthcare. Patient stratification for personalized treatment plans, disease subtype discovery, anomaly detection in medical imaging, gene expression analysis. Finance. Fraud detection through unusual transaction patterns, investment portfolio optimization, credit risk assessment, customer profiling for targeted services. Content organization. Document clustering for information retrieval, recommendation systems based on user behavior, image organization, news aggregation. Clustering algorithms have transformed how organizations derive insights from their data across numerous industries. By identifying natural groups within complex datasets, these techniques enable more personalized services, efficient operations, and innovative product offerings. The flexibility of clustering approaches means they can be applied to virtually any domain where pattern discovery and unlabeled data is valuable, from social network analysis to urban planning and scientific research. Key takeaways: clustering techniques. 3 core algorithms. K-means for spherical clusters, hierarchical for nested structures, DBSCAN for irregular shapes and noise handling. 4+ evaluation metrics. Silhouette score, Davies Bouldin Index, Hierarchical Index, and visual assessment techniques. Infinite applications. Virtually unlimited use cases across industries, from customer segmentation to anomaly detection and scientific discovery. Unsupervised learning, particularly clustering techniques, provides powerful tools for uncovering hidden patterns in unlabeled data. By mastering these algorithms and their evaluation metrics, you can extract valuable insights that would otherwise remain hidden in complex datasets. As you apply these techniques to your own projects, remember that the best approach often combines multiple algorithms and evaluation methods, guided by domain knowledge and clear business objectives. The field continues to evolve with new algorithms and applications, making it an exciting area for ongoing exploration and innovation. Thank you, and coming next, dimensionality reduction. We truly value your participation in our learning journey together. We will continue with Module 4 in the upcoming session. Dimensionality reduction techniques in unsupervised learning. We'll examine PCA, SVD, and other essential techniques with real-world applications. From image processing to recommendation systems. Stay connected. Subscribe, like, and share for more educational content.